So in the last video, we had looked into what are the problems where segment tree can be relevant, but we had not really discussed about what segment tree is, right? So in this video, we'll be starting about what segment tree is and how we can use them in our problems. Okay. So just to understand things, let's discuss a problem. So let's say you are given a array. So there is an n-sized array which is given in a ARR. Okay, so it will be an array, and you are given q queries or q operations to do on the array, which is like there is first type of operation which gives you a position and a value. So you need to change the value in this array at position x into v, like whatever there was previously, you just replace that with v. Or there is a second kind of query which is L and R. So in that case, you need to find the sum of elements which is in the range L to R in the array. Okay, so suppose this is some, let's take an example. So let's suppose you had 2, 3, 4, 2 again, and then some 5, let's say. Okay, so suppose you have like a query from, say this is 0 index. Let's take this 0 index. So if this is 0, then this would be 1. So this is 0, this would be 1, 2, 3, and then this will be 4, right? So if I give you a sequence of queries such that 2, say 1, 3, and then 1, 2, 4, then again 2, 1, 3. Suppose you want to execute the queries in this order. So this would be like finding out sum from 1 to 3. So that's sum of elements from 2 to 4. So that would be just 9, right? So this will give you an output of 9. Now this is an update operation, right? So you update a cell. So this is like a first type of query. So if you update the cell, there is no output, but the array gets updated and you have now 4 over here, right? Like this array over here changes and you have 4 over here. So this position is now not relevant from the previous case, and it has 4 in over here. And then when you do the same query again, the value has actually changed, right? So now the sum would be 2 plus 4 plus 4, that is 10, right? So the thing is, as you do updates, your answers for the same query change. So you cannot kind of like make a pre-processed prefix sum and solve the problem, right? So this is the this is a problem that we discussed in the motivation video, and this would be something over which we would be building the segment tree. Okay, so now let's look into how we can solve this problem. So the idea is we try to create a tree over an array. Okay, so we try to create a tree over an array such that each node is responsible for some aggregate, like sum or some kind of functions of the values which it is responsible for. So let's look into what we are actually trying to do. Okay, so let's take this array, let's take this 8 element array. Okay, just for example. So we want to create a tree on this array so that each element is responsible for some range. Okay, so these are 0 index. So let's suppose this root element of the tree is responsible for the element from 0 to 7. Okay, and this range can be divided further into 2 sub ranges, right? Like if you divide it from the middle, it can be divided into 2 sub range, which would be like 0 to 3, and then this would be something like 4 to 7, right? Like you can divide it into 2 sub ranges. Okay, so again you can divide this further if you want. So this would be like 0 to 1, and this would be like 2 to 3. Okay, so 2 to 3. Similarly, you have 2 nodes for this as well. Okay, so we don't even, so there will be something like 4 to 5 over here and 6 to 7 over here. So we are not really worried about this part. So we can even further divide these into smaller nodes, right? Like this would be like the leaf nodes, where you have something like 2 to 2, right, and 3 to 3. So every such node will be decomposed into this, right? So now what we do is that these leaf node contains the element that is present in the array. So this 2 to 2 will contain the element present at 2. So that would be 2, right? 3 to 3 will contain the element that is contained at 4, okay? So similarly we have all other values in all other nodes as well in the leaf case, in the leaf nodes, okay? Now for the nodes that are internal, like these are called internal nodes in a tree, which are not leaf, okay? So these nodes contain some kind of aggregate of the nodes which it is responsible for. So these are the two child nodes, right? So it contains the sum of the values that are contained in these two child nodes. So this will contain 6. So you can fill up these values as well. So 0 to 1 will contain 5, because the two leaf nodes will be 2 and 3, and that contains 5. So 4 to 5 will be 5 plus 1, so that would be 6 again, and 6 to 7 will have 4, right? Like this will be just 4. So again this node will contain the sum of these two elements, so that would be 6 plus 5, that is 11, and 6 plus 4 would be 10, right? And these summed up on to this node will be 21. So as you can see, 2 plus 3 plus 2 plus 4 plus 5 plus 1 plus 4 comes out to be 21, right? Yep, it does. So this is the tree that we are building up. So this tree that we are building up over here is nothing but what we call as segment tree, okay? So this tree is called segment tree, okay? So segment tree has a lot of nodes, and it is responsible for some childs, and each of the nodes is responsible for some range in the original array. So it's like, you can think about this in this way, that each node actually represents the sum of some particular range, right? So that's what this segment tree is storing. So segment is like a segment of the array, and it stores some aggregate over the segment. So that's what segment tree does, okay? So this is what we are building, okay? So now we will try to see what we will do with this segment tree when we want to, suppose, answer some query, okay? So let's quickly make up a smaller, like, I would not be filling out the values, but I hope you have got the idea of how to fill the values. We are not even considering how to code this, so the coding part is something separate. How do we create this tree and all is something different. But let's suppose we have a tree, okay? We can always assume, and then later on we can code it up, okay? So I'll be showing you how to code this up. Okay, so we have a tree, and these are, say, leaf nodes, right? So for this cases, we are taking everything as a complete tree, right? Like there are 8 elements, so we can build a perfect binary tree. So even if there are no leaf nodes over here, that's perfectly fine, right? Like these can be filled in with zeros, and they don't even affect you. So those are not really a problem. You can always extend the array filled with zeros and make it like a non-used element, something like that, okay? So that's not a problem for us. So now, first thing to keep in mind is that how many nodes does this tree have? How many nodes does this tree have? So suppose the original array had n elements, okay, n elements. So how many nodes does this tree have? So there would be n leaf nodes, right? N leaf nodes. Plus every 2 leaf node will combine into 1, right? So something like n by 2. Plus every 2 nodes in this level will, so there are these many nodes in this level, okay? This is the level. So now these nodes will be merged into a next level, so that will contain n by 4, plus so on, right? Like up to until it becomes 1. So this sum is nothing but 2n, right? This comes out from using the GP formula, okay? So there are exactly 2n number of elements, or even to be precise, there are 2n minus 1 number of elements, okay, if there are n elements in the leaf, right? So this is something to keep in mind. So we are not going overboard. So number of internal nodes is actually quite less, like there are only n minus 1 new elements that you are forming, okay? Okay, So let's create them back. We can do it a bit more. Okay, fine. So now, why are we even building this? Okay, so suppose you have some element over here, so that was responsible for these. Okay, like suppose there was 11 over here and there was 21. Okay, something like this. Okay, so now suppose you want to change some element in the array. Okay, you want to change, so suppose there was 4 in some position, which we have marked over here. So this is the tree right now, something like this. So suppose we want to change 4 to 5. Okay, so that means this leaf node value is going to change, right? That's what it means. So this array is nothing but the leaf nodes in some sense. Okay, so that means this leaf node value is changing. So which all values do you think in this tree will change? Which all values will change in this tree? Only those which are ancestor of this 4 node. Why? Because these contain some aggregate, right? And only these node contain 4 in its range. So only these will be responsible for some kind of change that happens in the node 4. Okay, so what we can do is that we can do some kind of DFS or something like that and go in this tree, finding out the position for 4, update this as 5, and then while tracking back we can like update this as say 7 because it increased by 1. Then we come back to this and we update it as 12, and we come back to this and update as 22, right? So in this way we can like change everything in the segment tree by changing very few number of nodes, right? So this is what we are trying to do. So now this structure, this tree structure is maintained even after changing a particular value, right? The tree structure is still intact even after changing particular value. So we have handled the first kind of query, that is 1xv, which changes the position x to a value v. So that can be handled in such a way, and in such a way that you can you maintain the property of segment tree, right? That every node contains the aggregate of its responsible leaf nodes, right? So for this node, the responsible leaf nodes are these, right? These 4 nodes, right? Something like that. Okay, so that's the first query, right? So we are updating everything and still we have the segment tree structure intact. Okay, so now we have the second kind of query. So that query is nothing but 2LR, right? So why are we even building the segment tree? So this update was anyways easier in array, right? If you have even had an array, you can update in order 1, but there should be some help in this query, right? Then only we have some benefit. Okay, so now we think about this in this way, that suppose you have like a query for this whole range from we have 0 indexed, so this will be 1. Okay, so from 1 to 7. Okay, so this is your query range. So this is like 2LR that is given to you, right? So you can see that, so you had to sum these 7 values, right? These 7 values would have been summed up if you wanted to find out the sum. So instead of taking these two values into consideration, we can directly use this value, right? Because we know that this node contains the sum of these two, right? And we want to find the sum of these nodes. So we can directly take that value from this node, right? Also for these 4 nodes, we can directly take the value from this node, right? And for this node, we can take the leaf node itself, right? So as you can see, we don't even need to iterate on all the elements in the leaf. We can use some kind of some nodes which are quite up in the level, and use the value stored in those to find out the sum. Now in the next part, we'll be seeing how these complexities are getting reduced. Like so there are still a lot of nodes, right? So you have to find them and then search their values, and then after you have found those nodes, you can easily add up the values stored in those nodes, but you have to find them and how many nodes will be there and so on. So in the next part, we'll be seeing how we can think about why is segment tree even optimizing these queries. So in array, you normally had this as order 1, right? And in when you had to add, you had like order n, something like that in normal array. So if segmentary can improve on this, then only segmentary makes sense, right? So in the next video we would be seeing at how these building this segmentary is actually helping us in the complexity part. Okay, see you in the next part.